And what I want to do first is I want to take a look at this chart that I have up. I had a couple email messages from people yesterday that are a little confused on the chart, a little confused on these refrigeration diagrams. So I want to just take 5 minutes. That's all it's going to take, if that, to go through this. Let's start with the easy part. Okay, where would I draw my line of where the pressure changes? Where's my 2 points of pressure change in any chart?
The condenser and the metering device, right?
Compressor and metering device,
Compressor,
right?
I'm sorry, yeah.
Okay. So if I draw my line of pressure change sort of like that, okay, I mean, I'm going right through a gauge, but everyone should be able to see what I mean by that. Okay, where is my 2 points of change of state?
Would that be the evaporating condenser?
Yeah, basically, the evaporator and the condenser. Okay. Granted, it's a little bit more slanted than that, but everyone sort of gets the idea.
Say it with some confidence, Rob. Come on, boy.
Okay. So, if I'm taking a look at the pressures, okay, TP2, TP3, TP4, what's going to be my pressures in all of those? TP2, TP3, TP4, what's my pressure?
100.
100? Yep.
Yep, it's on the same side of the compressor and the metering device. TP5 and TP6, what's going to be my pressures?
17.
Would it still be 17?
Yep.
Okay,
Why?
Because the pressure stays the same, right?
Pressure's the same. Okay. Now, we have to find a temperature, right?
Right.
Between TP2 and TP3, does my temperature change at all?
No.
No, because all that's going on is a latent heat change, right?
That's right.
So TP3, I can fill in my temperature.
I had a question for you, Chris, that you never asked.
Yeah, go ahead.
When you did this online, you changed the R12 to R22.
Yeah, this time I'm not, because I wanted to start with a blank chart.
All right.
Just a different way. Does the refrigerant really matter other than the temperature pressure conversion?
No.
No. Okay. So if I have 90 at TP2 for temperature, I have 90 at TP3 for temperature. What about the temperature at TP4?
Also 90.
Should be around the ambient temperature.
No, it's not. It's not.
Oh, you can get next week. Watch this. This week, watch this. And it run, bitch.
It'll be 78.
Yeah, this motherfucker.
Okay, I'm going to block some background noise.
Yeah, please.
You hear that, bitch? Got it.
Hey, folks, unmute yourself if you need to ask me a question or want to contribute in the conversation, but I really have to lose the background noise, especially when it contains language that isn't quite appropriate. TP4, what's special about that temperature? There's something really important here on that temperature.
That's so cool.
The subcooling, right?
Yes.
Okay, so subcooling is a decrease in temperature after my condensing temperature. Okay, so we do the change of state, we decrease the temperature after my condensing temperature. So what am I going to put on the temperature line for TP4?
78.
78.
How do you get 78?
78 or 88?
78.
100 minus, or sorry, 90, yeah, 90 minus 12.
88.
78. I think, yeah.
No, it's 88.
That's 88.
90 minus 12?
90 minus 12
Oh,
is
90. I
78.
thought it was 100 minus 12.
You said
No,
100
because
minus 12.
100 is the pressure.
Okay, yeah.
Okay, so we have a further decrease in temperature.
Did you say 100 at first?
He
Yeah.
did.
I
That's
admit
why
it.
we got the
You guys
88.
got me confused.
Okay.
Okay, but okay. Does everybody see this before I go any further in this? Is there any questions?
No.
Now, there's one more number that I can fill in on the left side of this chart. What is that?
The
What is the
superheat?
one? What?
Yeah.
Superheat?
Superheat, but for which pressure point?
TP1? I mean,
That is the
TP2.
old-
Sorry.
No,
TP2.
TP1, you had it. That is the only place that I have superheat.
Oh, that's right. The TP2 is after the. Okay.
Remember, condenser, what are my three functions?
D superheat, condense,
Superheat.
subcool. My
Yep.
bad, correct. You still my man.
You good, brother.
Okay. So is there anything else that I can do on the left side of that chart between TP1 and TP4? Anything?
How do you
I
get
got
the
a-
50?
The superheat should be
Oh,
50.
yeah. No, once again,
I had partially filled out, right?
the temperature, my condensing temperature, difference from the line temperature. Questions?
I thought superheat you had to add the temperature and the pressure to get the superheat. That's what I thought.
No, anytime you're dealing with superheat or subcooling, you're only dealing with the temperatures. So you converted the temperature to pressure
Okay.
at my condensing point. That gives you my condensing temperature. Think back to one of the first things I said when we were talking about gauges. Do I really care about the pressures? The pressures are cool to give me the temperature. And the pressure only tells me the temperature of 2 points in the system. Let me change that to a circle. My change of state, my condensing temperature there, and my evaporating temperature there. That's what those pressures are telling me. Okay. Quickly, and I don't want to get deep into it because we haven't done the PowerPoint on this yet. Okay? But the other side of the system, TP5 and TP6. Okay, between TP5 and TP6, do we have any temperature change? And it's okay to be wrong.
Well, yeah, the evaporator starts to heat the refrigerant up inside the evaporator, right?
Right, but between these 2 points, I'm boiling off refrigerant, right?
Okay.
So it's a latent heat change. Do I have a change in temperature any place where there's a latent heat change?
No.
No. Okay, so my temperatures at TP5 and TP6 are going to be the same. Now, we have a problem. Your charts do not have, or some of your charts do not have R12. The chart in your textbook does. But the charts that I gave you the other day as a handout do not have R12. So I went online, okay, I just looked up R12 temperature pressure charts on Dr. Google and found a decent temperature pressure chart. Okay, this one's actually pretty neat. It's at HudsonTech.com, and you can actually select the different refrigerants, which is sort of neat. But so 17 PSI, which is what we're looking at, is very close to 17.7. Can everybody accept that?
Yes.
17 PSI is very close to 17.7. So we are going to use 15 degrees as our temperature conversion. Everybody okay with that? Okay, because we have 17.7 PSI. Come over to the left to the Fahrenheit, okay, temperature scale. We have 15 degrees. Okay, so for TP5, let me just move that up to where it belongs, okay? Don't have anyone put it in that blank. There we go. Okay, and TP6, I have an evaporator of 17 or 15 degrees. Why does this not make sense in air conditioning? Why don't I want an evaporator 15 degrees in air conditioning?
Because it'll be frozen if that's the case. It has to be at freezing or slightly above or below freezing.
It's going to be a frosty evaporator, okay? This is more something you'd find in refrigeration. But you know what? It's still good. The chart's still good. It still gives you an idea of what's going on. Now, you will notice that I left temperature 7 blank. Why did I leave temperature 7 blank? Some of you have gone ahead in your reading or looking at course material. So tell me, why did I leave temperature 7 blank?
Because of superheat.
Yeah, well, superheat is 14. So what do I have to do to the temperature at that point to get a temperature reading? I have to add it because superheat is additional sensible heat that is added to the refrigerant in the last pass of the evaporator and in the suction line. So what is my temperature at TP7?
29.
29. Okay, and again, we're going to talk more about superheat tomorrow. Now, TP1, gas or liquid or saturated? Down here at the bottom. The gas. Okay. TP2 and TP3.
Saturated.
I'm going to go with saturated because it's in the middle of change of state. TP4.
Liquid.
TP5. Careful.
Saturated.
Okay. Be very careful here, guys. Some of you are going to be... Guys, be very careful at this spot, okay? If you are taking the EPA exam, which all of you will be, okay, I want you to very carefully look at the multiple choice questions in this spot. Some of your exam versions will say flash gas, which is not a choice on here. Some of your exam versions will say a low pressure liquid. Some of your exam versions will say start of saturation. Just be very careful here because they're all correct answers. It's the start of our saturation, it's a low pressure liquid, and it's a flash gas at that point. Does anybody have any questions for me? We need to be very careful there because I don't want anyone to come back and say, you gave me the wrong answer, okay?
So that's for TP5?
That is right as we come out of that metering device. Okay, so for TP5, you'll notice I put it in the middle between saturated and liquid because it could be considered the start of the saturated. It could be considered a low pressure liquid, and it's also called flash gas. I don't want anyone to... What?
Wouldn't flash gas just be a component, about a 25% of what it is at that point?
Yeah, but again, a lot of people refer to it coming... What was that?
Well, I said I understand it contains it, but it would be misleading if I saw it as a test question. If they asked, specifically, is it flash gas? Not entirely.
They won't ask it in that way. They'll ask, what's the state of the what is the refrigerant as it comes out of the metering device? And it will only give you one of those options, and then some other wrong answers. But okay, just be aware there's an issue there. Okay.
Yeah, good to know.
Okay, the EPA exams, they're going to ask you basic questions about the refrigeration cycle. TP6, what's my state of refrigerant?
Saturated.
It is saturated, yeah. TP7, what's my state of refrigerant?
Back to
Yes.
gas.
Any questions whatsoever? Honestly, folks, there's nothing here as a question that doesn't need to be asked. If you have a question, I guarantee one of the other 40 people here have the question too.
Yeah, I got a quick question. Kind of not relative to this, but on PDF Expert, I can't seem to rotate the document.
It is, believe it or not, even on your iPad, there's a menu there that has rotate current page left or right.
Okay. I'll try
Take
to
a look
find
at that, and I'll make a note to toss a screen print up later of exactly where that is. My iPad,
Okay.
I hate to admit, ran out of battery last night.
All right, no problem. Thanks.
I'll put a screen print up later.
When I went to submit my assignment yesterday evening, it would not submit, and I had to take a screenshot of my laptop with of my iPad with my phone, send the photo to my Facebook, save the photo from my Facebook onto my iPad, and then upload the photo. It was really annoying.
Is that the first time that has happened to you?
Yes.
If that ever happens again, could you grab a screen print of the error that's it being given? Because you're the second person that told me about that.
It's not giving any error. It's not even giving you an option to submit. You go back, it doesn't do anything.
That is weird. I'll ask IT about it. You were trying to submit one of these refrigeration sheets?
No, it was the lab.
Oh, okay. Okay, yeah, I'll ask IT to take a look at it because somebody else in another program sent me an email on that this morning as well. Sorry about that, Dylan.
No, that's all right.
Okay.
Hey, Chris, do you still have to go over more of the superheating and?
Oh yeah, that's
okay.
Tomorrow's lesson.
Okay, so I was still just a little confused on where you get the numbers for that. And
For TP7?
Yes.
In real life, you would put a pipe clamp thermometer onto the suction line.
Okay.
Okay, that would give you the temperature of the suction line, which would come out to be, in this case, 29. We know what our boiling point is because of our pressure of 17, which converts to 15. With me so far?
Yep.
In real life, the number you are trying to get is 14. So you would take your suction line and subtract your boiling point temperature to get your superheat.
Okay.
Now, why that matters, we'll go much more into tomorrow.
All right, so if I'm not completely 100% on this, wait until to be done with tomorrow's class to fully.
Oh, yeah, and I extended all the due dates on these, if I remember right. I went back and extended them all because we're running a day behind.
Okay, thank you.
Okay. Folks, I'm going to pull this off my screen, but just, again, this hopefully clears up some of the emails that I've gotten on this. Okay. Now, I do need to talk today about, I really need to talk about metering devices today. We started briefly on it yesterday. Let me pull up that PowerPoint. And let me get to the place where I want to be. This is a slide we left off on. Which metering devices did I tell you you're going to most often see in air conditioning?
The first one.
I'm going to see the first one, right?
Yes.
What other ones am I going to see in air conditioning most often?
TXV.
Yup, I'm going to see the TXV. And I made a comment about by the time you guys are in the field, through your apprenticeships, you're going to start seeing a lot more of what metering device?
Electronic.
EEV? Yeah, EEV.
The EEV. Now, what metering device did I tell you a lot of units are shipped with?
AXP? Yeah.
AXV, you're never going to. AXV, you will not see in air conditioning. How about the metering orifice? It's called a fixed orifice.
Yeah, fixed orifice.
Okay, very inefficient, but they still ship them with it. Cap tubes, primarily window units. TXVs, primarily our split systems and our rooftops. Metering orifices, a lot of the older systems, a lot of the heat pumps, a lot of R22 systems. Electronic expansion valves means you're rich and you can afford great equipment. What it boils down to. Or you live in California. Okay, fixed and metering devices, they're the simplest type of metering devices out there. It is a fixed diameter passage, okay? It's not going to adjust itself for heat. There's no moving parts, okay? And it's just there. It takes no temperature into account. It takes no load conditions into account. It doesn't care less about how much it's having to cool off. It is always just there. It meters the same amount of refrigerant all the time as long as the pressures remain constant. There's two types of fixed metering devices, the cap tube and the metering orifice. These a lot of times are referred to as fixed orifices. Okay? You see them in the vendor's manuals as fixed orifice. By the way, the vendor manual is shipped with every unit. Where do I normally find it when I go out on a job site? The installation instructions. Where do I normally find them?
Inside the unit.
Yeah, most often they're inside the unit where they were shipped, and guess what? They're still sealed in the plastic bag it was shipped in. So it tells me how many people actually glance at the installation instructions. Don't be that tech. Okay, always glance at the installation instructions. Cap tubes are used extensively, and honestly at this point, I'm removing that first one, and I'm saying window unit air conditioners. You still see them in older refrigerators, but in the newer refrigerators, believe it or not, refrigerators have actually stepped ahead of the energy efficiency curves, and a lot of them are now using a lot of the electronic metering devices and TXVs and stuff like that. Home appliances have gone to the top of the efficiency curve because that's the only thing that separates them from their competitors, is how efficient their equipment is. I can get great efficiency out of changing my metering devices. So primarily in air conditioning, you're going to see cap tubes in window air conditioners. Metering orifices are used heavily in heat pumps. And when we start talking about heat pumps, I'm going to explain why. We also see them used in older, inefficient split air conditioning systems. The rate of flow of refrigerant through a fixed metering device is relatively constant, okay, when the compressor is running. Anybody want to take a guess on why we use them in heat pumps? And again, wrong answers are okay. Does anyone want to take a guess why we use them in heat pumps?
Probably because they're so inefficient that they let heat escape better.
Well, again, we haven't talked about heat pumps yet, but heat pumps, the refrigerant flows in two directions. Does a little hole care which way the refrigerant is flowing?
No.
No. Okay, so they're very cheap to use in heat pumps because you don't have to use two separate metering devices. Heat pumps don't care which direction they don't care which direction the refrigerant flows. Okay, so fixed orifices are used a lot in heat pumps.
I saw a thing about heat pumps that had something similar to that, but it actually moved back and forth and regulated whether it flowed through several tubes, like capillary-looking tubes, or one orifice, depending on which direction it was going.
Yep, there's also fixed orifices with check valves.
Yeah, that's pretty cool.
I think heat pumps are cool to start with. There's a lot of people who think I'm sick for thinking that, but anyway, moving on. Metering devices that can change their orifice size to account for changes in cooling loads are referred to as modulating metering devices. For those of you who are taking notes in one way or another, modulating metering devices. Okay, all it means is that the metering device can change their orifice size to account for changes in cooling loads. Okay, all types of expansion and float type valves fall under this category. Modulating metering devices. Sounds like something you might find on a test someplace, a certification test or a licensing test. If you are thinking that, you are correct. Again, modulating metering devices, all it means, it's an expansion or float type valve that will change the flow, change the orifice size to account for changes in cooling load. Okay, because of their ability to regulate, they are much more efficient than the fixed metering devices. This is all about efficiency. Okay, there are government regulations out there for efficiency. Barry, if you are on the line, what is the required SEER rating right now in Pennsylvania? I don't know that number. Oh, he might be muted.
No, he don't have no microphone on.
Oh, okay. Okay. Most of the required SEER ratings right now are up near 13 SEER. Okay, I don't know what the Pennsylvania number is. If one of you guys on the York campus does know that number, let me know. But most of our required SEER ratings are running about the 13 SEER point right now. Barry, if you have access to your chat window and want to toss it in the chat box, go ahead and toss it there as well. Okay. So we are very concerned about efficiency at this point. And that is the reason why we've gone to these more efficient metering devices.
It's 13. I just Googled it.
Okay, it's 13? Cool. Okay, then there's, again, different states have different requirements, and before I toss a number out there, I really want to know. These valves are better suited for uses in applications that have load changes frequently. Okay, what do I mean by load changes? Some of you guys did have design last term, so you should be able to tell me about this. What do I mean about load changes?
Maybe change a compressor or condenser.
More thinking about building load changes. What do I mean by load changes? What happens when the kids come home from school and it's a nice warm day outside and they're always in and out? What happens to your air conditioning?
It's running nonstop.
It runs constantly. Okay, that's a high load environment. What happens on a night you have your air conditioning's running on a September day, and at night your outside temperature drops? What happens to the load on that building? It goes down, right? You have less of a cooling load. So the TXVs and the adjustable orifices automatically adjust the refrigerant flow to these changes in cooling loads. That's what makes them so efficient. Okay, they most often sense the evaporator temperature or your superheat, and they adjust based on that. Cap tubes, again, are metering devices. They're not adjustable. It's a seamless tubing. It's like 1/8 of an inch or lower diameter. Okay, The tube acts as a constant throttle on the flow of refrigerant. The pressure decreases as the small diameter restricts the flow of liquid refrigerant through the tube. Okay, it's like any pipe. You put a small pipe in after a large pipe, it's going to restrict the flow of whatever liquid down. Okay, well, it drops pressure as it exits that small tube. As the pressure drops, a small amount of liquid refrigerant starts to evaporate in the tube. The vapor that is produced by the drop in pressure is known as flash gas, and its formation provides a sudden drop in temperature in approximately the last quarter of the cap tube's length. This is where we start boiling off our refrigerant in a cap tube system. This is an example of a capillary tube. Now, think about this thing. It looks bigger on the screen than it actually is. Okay, these things are 1/8 of an inch, a 32nd of an inch hole in the center. These are very, very small. Okay, the performance of a cap tube depends on the tube length, the inside diameter, and the number of turns in the coil. Why do I say the number of turns in the coil? Why does that change the flow of refrigerant? Anybody?
I'm guessing you count how many times you have to in the wire.
Does refrigerant flow better in a straight pipe or a curved pipe?
Straight pipe.
Yeah, any fluid is going to flow better in a straight pipe. So why does the number of turns in a cap tube make a difference?
Because it slows the pressure.
Yeah, I think all of you said the same thing. It slows the flow of refrigerant. It's a restriction. Okay? So the number of turns, the length, the inside diameter, the number of turns in a cap flow determines how much pressure drops between the condenser and the evaporator. I have the high pressure coming into the cap tube, and then these three components, these three characteristics of the cap tube make a difference. It tells me how much pressure drop I'm going to have. The longer the cap tube, the greater the pressure drop. The smaller the diameter, it should say the greater the pressure drop. Smaller diameter. Okay, that should say the greater the pressure drop. Let's correct that for anybody taking notes. Again, small diameter, I'm restricting. Turns create friction as the refrigerant flows and creates additional pressure drop. All three things. The longer the cap tube, the smaller the diameter, the greater the pressure drop. Okay? Turns add additional pressure drop. So when you think about those two things, okay, cap tubes is just like a garden hose. I'm not going to have as much of a pressure drop with a 25-foot piece of hose as I'm going to have with a 200-foot piece of hose. Okay, the longer the hose, the greater the pressure drop. Okay, and again, the difference in the bore, which is the definition of the center, the bore, okay, all is going to give me different pressure drops and different flow rates. In some applications, the cap tubes serve the function of both the metering device and the liquid line. Look at any older window air conditioning unit. The cap tube is directly connected to the condenser, and it is the path of refrigerant between the evaporator and the condenser. Okay? The cap tube serves as both the liquid and the metering device. There's no big issue with this. Hey, it's a small system. They're what, like 12 inches apart? Okay, if the distance between the evaporator and the liquid line or condenser is shorter than the required length of the cap tube, a portion of the cap tube can be coiled. This is all engineered. Okay, you can't guess on cap tube lengths. Okay, a fine filter or filter dryer is usually installed between the liquid line or condenser and the cap tube. We want to filter that refrigerant before it goes into the cap tube. This filter dryer helps prevent contaminants from entering and clogging the cap tube. Okay, how do contaminants get into a refrigeration system?
The technician.
Technicians, when they're putting their gauges on and off. How else do the contaminants get into a refrigeration system?
Like mowing the lawn if you don't put the caps back on the refrigeration lines?
Well, yeah, if the caps aren't on, but again, yeah, that is very valid, and I'm going to attribute that back to a technician, because who's responsible for putting the caps on the refrigeration system? The third one I'm looking for
Compressor replacement.
Is also attributed to a technician, but it is more on the installation side. Okay, again, the third one I'm looking for is also attributed to a technician, but it is more on the installation side. Can anybody tell me what it is? I think some people in here have had that class already.
You didn't seal it right?
Replace the compressor. Or did maybe
I didn't seal it right, and I didn't hear what about the compressor?
Replace the compressor.
Yeah, and they didn't do something when they either installed the system or replaced the compressor. They didn't do something very important.
They didn't vacuum it right.
Well, vacuum will remove moisture, okay?
Right.
Does vacuum remove hard particles?
No.
So when they braise or cutting the tubes?
When they brazed. What about when they brazed? That is exactly where I'm going. What didn't they do when they brazed?
Check for leaks.
They didn't take the shards off the end of the cuts.
Purge with nitrogen.
What was that? That was what I was looking for.
Purge with nitrogen.
Purging it with nitrogen as they're brazing. All of you who are going to have piping, that's our 1316 course, okay? When you're doing brazing, you're going to be taught how to use nitrogen to have a continuous flow of nitrogen through the copper lines while you are brazing. What that does, it prevents the buildup of the black film. Okay, it prevents the oxidization that happens when you braze. Okay, and it keeps the inside of the tubes clean as you heat them and braze. So you're all going to be taught how to use nitrogen as you're brazing. If for some reason an instructor or shop person forgets to talk to you about that, make sure you ask them to show you that. Okay, it's critical. If you're brazing refrigerant tubing, you have to use a flow of nitrogen to prevent buildup of crud on the inside of the tubes. That's what I was looking for. That will clog every metering device out there. Okay.
Yeah. Didn't you say with the filter dryer, if you have to replace the metering device, you're supposed to replace the filter dryer every time? Or whenever you clean the system, you're supposed to replace it?
Yeah, anytime you open the system, okay, you should really replace the filter dryer. Okay, now, here's the key. And you're not going to, by the way, in our shops, you're not going to see us replace the filter dryer every single time we open the systems, okay? The reality is we open the systems like 20 or 30 times a term, and we don't replace the filter dryer every time. We put a good vacuum on the system, and we probably replace them twice a year. But just so you're aware, okay, if you're in the field, we want that filter dryer replaced any time you open a system.
You also said about putting the filter dryer on the vacuum line if you have just like worked on the system had a bad compressor.
Yeah. Did I say vacuum line or did I say suction line?
I'm sorry, suction line.
Okay, yeah. If you've had a burnt out compressor, that actually the windings burnt down because of acid and stuff like that, yeah, you put a filter dryer there as well.
But it's not on there long.
What was that?
So you don't keep it on there long.
Well, they're not designed to be permanent fixtures. Let's just put it that way. When you go in the field, are you going to see them left on systems? Yeah, because once again, to remove them, what do you have to do? You have to cut open the line. You have to recover refrigerant. So a lot of times what technicians do is they will come in here, they'll put their suction line filter dryer here, okay? It has a replaceable core. So they'll come back probably 2 weeks later and replace that core with a new core. And they'll leave it.
Does it have shut-off valve that prevents the... Yeah.
Yeah, and if it doesn't, you make very sure it does when you install these things.
And you will use a little bit of refrigerant opening that up to replace the core.
Well, legally, you shut the valves off and you actually recover the refrigerant out of here because these things can hold a pound of refrigerant.
Oh, wow.
Okay, so legally you don't lose any refrigerant at all.
So there's
I'm not going to go in, and I don't want to get... Dylan, go ahead, what?
So is there a recovery port on that?
Yes. Yeah. Okay, I don't want to get too far off topic on this, but when we talk more about pump down systems, when you pump a refrigeration system down, okay, there's no refrigerant in this area, or very little, so that makes it easy also. Okay, but again, nitrogen is a very important part of this. So the cap tube, again, in this situation, we have our condenser, we come out of our condenser to our filter dryer. We might have the cap tube with coils and stuff like that connected directly to that, and it goes into the evaporator. Cap tubes can be installed so that a portion of it is in contact with the suction line. We're looking for heat exchange. Okay, we want to cool the liquid refrigerant as much as possible before it goes into the evaporator. This gives us better heat capacity, okay? It actually makes things more efficient. So again, we could have the cap tube that is directly connected to the suction line. What this does is two things. One, it cools the cap tube, and the second thing it does is warms up the suction line before it goes to the compressor. So if there's any liquid refrigerant that comes out of that evaporator, because the cap tube can't regulate the flow of refrigerant based on load, okay, it actually gets rid of that liquid refrigerant before it hits the compressor. Because compressors cannot pump liquid, they're vapor pumps. Cap tube systems, no check valves. Refrigerant can flow in either way. They're used on small, fractional horsepower hermetic compressor systems. They cannot have an overcharge. Okay, you're going to hear me say occasionally, a critically charged system. Again, a critically charged system. There's an exact amount of refrigerant that that system must have. It cannot have an overcharge. Okay, severe frosting of a suction line during the startup is an indicator of an overcharge of refrigerant. Think this is for troubleshooting tips, guys. Severe frosting of a suction line during the startup of a cap tube system is an indicator of a refrigerant overcharge. So that's cap tubes. Any questions on cap tubes? Okay. Metering orifices. This is where we start jumping out of window units and we start getting into the larger systems. Okay, a metering orifice, it's a fixed orifice. Little hole between the fittings inlet and outlet. Okay, it's installed between the condenser and the evaporator, and it provides that pressure drop. We all know by this time that if you shove refrigerant through a little small hole, it's going to provide a pressure drop. fixed orifice can be removed and cleaned for service. Okay, it's very important they're properly sized. They're not interchangeable between different system sizes. Okay, and the charge is critical. Okay, it is a critically charged system. In other words, if the system has a leak, can you just top off the system?
No.
No. Well,
Oh,
you
you have to
can,
fix-
but it's not the right way to do it. Someone started to say something. What do you need to do?
You have to fix it, I guess.
If a system with a fixed orifice has a leak, the correct method is to recover all the refrigerant out of the system, put it into a vacuum, and weigh in the replacement refrigerant back to the factory charge. Okay, do techs out in the field all the time just top these things off for leaks? Yeah, they do. But again, it's not always the right thing to do. And you're going to see this a lot in your apprenticeship, okay? This is a lot of the older techs in the field will chalk this up to the difference between school learning and field learning, okay? Just remember, when I'm giving you this information, it's my job to tell you what the right thing to do is, not the shortcut way to do things, okay? So just remember that when you're on your apprenticeship. When you say to your guy who you're working with, okay, who's taking you through your apprenticeship and training you, okay, well, my instructor said you do this, okay? A, he's going to give you the finger, then you're going to get the lecture on school learning is different than field learning, okay? And you might not be a very popular person at that point. So just remember, I have to tell you the right way to do things. So when you have a critically charged system, okay, and you have a leak, or you have a low charge, well, there's a leak someplace, okay? You've got to recover the refrigerant out of the system, put it into a vacuum, and recharge it according to the factory default charge. Where are you going to find the factory default charge?
In the manual.
Either in the manual or on the nameplate, on the data plate that's on the unit. It says it. Okay, so couple different types of metering orifices used in heat pumps. Again, we'll spend more time on this when we talk about heat pumps. Okay, it's a bidirectional orifice. It's called a piston type. This was the one you were asking me about earlier. Okay, it actually allows refrigerant to flow in both directions. There's a little moving part inside. That's called a fluted piston. When the refrigerant is flowing this way, okay, it comes through the center of the orifice. It blocks the bypass. When the refrigerant is flowing this way, okay, it allows refrigerant to flow in multiple directions.
So what makes this not efficient?
Because it still can't tell, it is either all or nothing in each direction. Okay, it's not metering. Can't change the quantity of refrigerant. Okay, so this little orifice in the center here, where I just drew my arrow, doesn't get larger or smaller based on the load on the system. Okay, it's still a fixed orifice.
It's
Does that
surprising
answer
that
your
they
question?
couldn't figure a way out to put some sort of adjustment valve in there.
Well, they sort of did when they started using the TXVs. Okay, the metering devices are installed again between the condenser and the evaporator. Okay, one metering device meters the refrigerant flow in a heat pump during the cooling mode. There's another metering device that meters the refrigerant flow during the heating mode. Okay, again, one acts as a check valve for the metering device, and one allows the refrigerant to flow freely. Refrigerant changes direction. That is the end of the fixed metering devices. Okay, you have two types we're worried about. Cap tube and the fixed orifice. Any questions on those two? Because now I'm going to get into the TXVs. TXVs is basically what you're going to live with from here on in. Okay, and again, we're going to move to electronic expansion valves very fast as the price on them comes down. Okay, TXV is a temperature-actuated metering device. You will also see them listed in your reading material as a TEV. It's the same device. Okay, TXV, TEV, interchangeable. Okay, the valve mechanism responds to load variations. The purpose of the TXV is to keep the superheat of the evaporator coil constant. Okay, now, we have not really spent a lot of time talking about superheat yet. The superheat is this number right there. It is based on the temperature rise that happens in the last pass of the evaporator after the change of state. That is the superheat. It's the sensible heat gain following the change of state from a liquid to a gas of my refrigerant in the evaporator. Now, without getting into too much details, what would happen if instead of ending here, my liquid refrigerant was all the way up to there? What would happen to my superheat number?
It would go up.
Or, better,
Down.
Yeah.
it would go down because I have less room for the sensible heat gain. Now, what would happen if my liquid, if the change of state ended there instead of there? What would happen to my superheat?
It would go up.
Why?
Because of pressure.
How about because I have
Pressure
a
would go up too.
How about because I have a greater length of evaporator tubing to gain sensible heat?
Wouldn't the pressure also go up?
Not necessarily. I don't want to. I want you just to think about temperature on this one. Let's ignore pressure for the moment. Okay, so if I have this whole area for sensible heat gain, my temperature of the refrigerant is going to climb. Okay? So when we're talking about superheat, okay, and adjusting superheat and controlling superheat, all we are doing is changing the amount of refrigerant that's in the evaporator. And again, tomorrow we'll talk more about evaporators and that whole thing. But I'm adjusting superheat. I'm changing the amount of refrigerant that's flowing into the evaporator. Let me ask one final question before I go back to the other slide. Do I have more cooling potential? Can I have absorbed more heat with more or less refrigerant in the evaporator? Think about not just sensible heat. Can I absorb more? The more refrigerant I have in the evaporator, the more heat I'm going to absorb. Because the biggest part of heat absorption comes from my latent heat, not my sensible heat. So what do I use superheat for? Why do I care about superheat? What does it tell me about the refrigerant in the evaporator?
There's gas.
Turning back into the
Nice keep it gas.
Yeah.
Well, I just gave you two examples. If I have more refrigerant in the evaporator, my superheat is going to be lower, right? If I have less refrigerant in my evaporator, my superheat is going to be higher. So what do I use superheat for?
Determining the amount of
to know how much refrigerant is in the evaporator?
Yeah, it basically is my tool for figuring out how much refrigerant is in the evaporator. Okay, if my statement is true that I just made, the more refrigerant in the evaporator, the more heat I can absorb. Okay, why don't I want a superheat of 0?
The evaporator will freeze up, right?
More one you think about the level of liquid. Let's not think about superheat is 0. It just tells me I don't have any sensible heat gain, which would tell me my evaporator is completely full of refrigerant, liquid refrigerant. Why don't I want a superheat of 0?
The refrigerant isn't boiling off?
Which would do what? You're on the right track.
It'll introduce liquid refrigerant into the compressor.
That's exactly right. I gotta have a little bit of superheat. Superheat is my sole protection against liquid refrigerant into my compressor. Okay. So, back to this. All we are doing with a TXV is we are changing the flow of refrigerant to keep the superheat of my evaporator coil constant. So as the load increases, the refrigerant boils off faster. We have greater superheat. My TXV, and I'm going to show you this, opens, allows more refrigerant in. As the load decreases, the refrigerant doesn't boil off as fast. The evaporator gets more full of liquid refrigerant. The superheat drops. The TXV starts to close because it maintains a superheat. The TXV has a little bulb. You have 2 ports on a TXV, or sometimes 3, which I'll show you. There's a bulb. It's a temperature sensing bulb that's attached to the suction line after the evaporator coil. It's the evaporator outlet. The bulb must be insulated, and it must be mounted on a horizontal section of the line. Okay, the bulb cannot be installed on the bottom of the line. I'll show you a diagram here in a minute. Because the bottom of the line, the suction line, has some oil in it. Okay, so we have this is a TXV. We have our liquid line coming in. Our liquid refrigerant comes into the center here. There's an adjustable orifice in here that will open or close based on the pressure created by this bulb, the pressure created by an adjustable spring, and the pressure in the evaporator. Okay? Then we spray our refrigerant, low pressure refrigerant, into the evaporator. It boils off. It starts absorbing sensible heat, gets warmer. This bulb picks up on how warm the refrigerant is, and the pressures will change to regulate the refrigerant that's being allowed through the metering device. Okay? This bulb cannot be installed on the bottom of this line, or it will get messed up because there's a refrigerant oil that goes all the way through the system.
What's it made of?
What, the bulb?
Yeah.
It's metal. It's usually copper.
Okay.
This is a little copper line. It connects into a stainless steel or steel expansion valve head here.
Gotcha.
Okay. It's filled with a gas. Things don't work too well if you break this line or you kink this line. Okay. This is a picture of one, okay? You have the bulb. This is copper. Okay, this is all filled with a gas, connects into the top of the expansion valve, the head. This side goes, your liquid line comes in. This connects to your evaporator. This down here at the bottom is just the cover's off here, but there's a set screw down here. Okay? The sensing bulb senses the temperature created by in the suction line, and the force created by the bulb will open or close the valve. The fluid or gas inside the sensing bulb is called the charge. Okay, the fluid or gas inside the sensing bulb is called the charge. TXVs use 4 types of charges. There's a liquid charge that has a temperature that is the same temperature-pressure relationship as the system. There's a cross-liquid charge. It's a fluid that does not follow the same temperature-pressure relationship of the systems. They're mainly used on low-temperature applications. You won't see them much in air conditioning. There's a vapor charge, and there's a cross-vapor charge. The vapor charge is sometimes called a critically charged bulb. It has a very small amount of liquid, mostly vapor. Again, you don't see them much in air conditioning. Cross vapor charge, same as the vapor, but different temperature pressure relationships. Again, don't see them much in air conditioning. Primarily the one you're going to be dealing with, okay, is this liquid charge. Has the same temperature pressure relationship, because most of your systems are set up for either R22 or R410A. In refrigeration, we start doing a whole bunch of crazy stuff with TXVs and stuff like that. Now, having said that, are TXVs interchangeable between R22 and R410A?
No.
No, they're not. Cannot change a system from R22 to R410A, and I want you guys to sort of tattoo that in your minds for a future test you're going to have. Okay, it's going to probably be on your EPA test. It's probably going to be on a 410A certification if we get that far, which I'm hoping we do. Okay, I want you guys to tattoo that in your minds. Okay, you cannot change R22 systems to 410A. Okay. Again, just some different diagrams and stuff like that. I don't want to spend a lot of time on it, but it basically says this is my refrigerant pressure, and this is what happens when we use a cross charge, okay? And we can use the correct TXV on here to maintain our refrigerant, our superheats and everything. I don't want to spend a lot of time on the chart. It's really not necessary. It's in your book, too. Inside the valve body, there's a needle and a seat. The seat is usually made of a hard metal such as steel, so's the needle. The movement between these two parts creates the valve action. The seat is stationary. The valve needle moves, and this is what the inside of a TXV looks like. Okay, there's a little seat in here. There's a carrier in here, okay, that moves up and down into that seat. Okay, and if you look at the end of that carrier that I'll show you, right here at the end, there's a little valve assembly in here. There's a little bump in here. Okay, that helps up close basically the valve hole that's in the seat. Okay, so what's going on is you have your valve seat right here, okay, as the needle and the face of the needle move up and down, it either expands the opening or contracts the opening to allow more liquid refrigerant or less liquid refrigerant to come through here. Okay, so we have our TXV coming in. Okay, our refrigerant coming in. There's our little needle and seat arrangement in here. Okay, and our flow of refrigerant comes out here to the evaporator. And it's regulated by the pressure of this spring, which is adjustable. You as a technician can adjust this. The pressure of the bulb pushing down, which is adjustable based on the temperature of the suction side, and the back pressure from my evaporator. So there's 3 forces on a TXV. The TXV is a common. What?
What are we going to see more common on exams and stuff? Is it going to be called the TEV or the TXV?
You're going to see both, I hate to tell you. I have that bad news for you. You're going to see both.
Nice.
That's unfortunately, it is the way it is. I think I have Connecticut students on the call here. When I took my initial licensing exam in Connecticut, they had both on the same exam. Okay. When I took my refrigeration exam in Massachusetts, everything was TXV. When I took my EPA exam, they had both on the EPA exam. Pennsylvania, you guys, for the York area, you don't have a refrigeration license. If you go into Philadelphia, you have a refrigeration license. Okay, and they use TEV on that license exam. Maryland uses both TXV and TEV. They use the same exam as Connecticut does. So again, it's just dependent on where you're going to get licensed. Sorry guys, you got to know both. Okay. TXV is adjustable. This, I'm going to tell you right now, I need you to memorize this. I hate telling you guys to memorize things, but this slide is important. Turning the adjustment counterclockwise sends more liquid into the coil, which reduces the superheat. And I showed you that on when I looked at that diagram. The more liquid in that coil, the superheat is reduced. Turning the adjustment clockwise chokes off the flow of refrigerant and increases the superheat. Okay? Because again, less refrigerant, greater superheat. Do any adjustments extremely slowly and give the system time to respond. How long should I wait for any refrigeration system to respond to a change in TXVs before I make another change?
10 minutes?
That's what I'll say, 10 to 15 minutes.
10 to 15 minutes. Air conditioning and refrigeration, as soon as you get into adjusting valves, is, I call it the hurry up and wait trade. You're going to make an adjustment, you're going to wait. You're going to take your measurements. You're going to make another adjustment, you're going to wait. Take your measurements. Now, anyone want to guess the only times in the last 20-some years that I've had to adjust a TXV valve?
Twice?
No, give me a, why have I had to adjust a TXV valve in the last 20-some years in the field?
Oh, somebody messed.
Tried to adjust it first.
Somebody else went and adjusted it when they didn't need to.
Yeah, probably the homeowner.
Nope. Nope. Homeowners don't know where these things are, and we never tell them. Okay?
I'm a homeowner, and I do.
Yeah,
I was going to guess about maybe floods. You guys get a lot more floods down there than we do.
Yeah, but these are sealed components. I never need to touch them. Okay? And I've only been down here 6 years now. So before that, I was in the northeast part of the country. I lived in Connecticut.
Yeah, but you're a Florida now.
So anyway, guys, TXVs, you don't have to adjust that often. If you have to adjust them, you basically take them back to the factory settings. And 9 out of 10 times, if everything else is right with the system, if they're installed properly, they actually work the way they're supposed to, spec to the system. Okay. Ignore the pressures in here, okay, because it is still talking about R12. Okay, a lot of the textbooks still reference R12 on their diagrams, so ignore that, okay? That's not what I'm trying to do with this picture. This is what we call a valve in equilibrium. It has 10 degrees of superheat. There's a magic number I'm going to give you. Superheat should be between 8 and 12 degrees, always. Superheat between 8 to 12 degrees, always. Okay, so in this case, the valve is at equilibrium. Basically, the bulb pressure pushing down equals the spring pressure pushing up and the evaporator pressure pushing up. It has a perfect 10-degree superheat. Everybody see that so far? You with me? Okay, now the load conditions change. For those with kids, one of your kids leaves the sliding back door open on a 95-degree day. House heats up. The sensing bulb starts to warm up because all of a sudden that refrigerant in that evaporator is boiling off faster. The level of liquid refrigerant in my evaporator is falling because it's boiling off faster. I have more space for sensible heat gain. The valve is going to open because the superheat has started to warm up. It allows more liquid into the evaporator, which lowers the superheat. So again, now my bulb pressure has warmed up. It's pushing down based on the spring pressure and the evaporator pressure. Okay, so now we've opened. We're starting to open up. Our superheat is still high because it takes a few minutes for it to respond. Okay, so we're now opening up the refrigerant, increasing the flow of refrigerant into the coil. Superheat's too high. As the demand for cooling decreases, in other words, you close the door and the house cools back off, the bulb starts cooling off because now I have more liquid than necessary going into the evaporator. The bulb cools off. It takes pressure off the diaphragm and it closes the valve, decreases the flow of refrigerant, and that will eventually raise the superheat. So again, now the bulb has cooled. That whatever fluid or gas that's in here has now less pressure. So the diaphragm in here that controls this whole thing is pushed up because of the spring pressure and the evaporator pressure. We close this little valve that's in the center here, and we start blocking the flow of refrigerant. Okay, it decreases.
Does this have any direct correlation to the compressor? Like when the valve opens, on the expansion valve opens, does that kick the compressor on? No, compressor's running through this entire time. Okay. Can it change the amperage of the compressor? Yes, but not by much. Okay, what kicks? Think back to the electrical. What kicks your compressor on or off? Thermostat. Thermostat, yeah. With newer evaporators are much longer in length, not your physical dimensions, but the length of tubing. There's a pressure drop between the metering device to the suction side. Okay, based on the length and the number of turns and the number of coils in that evaporator, there's a pressure drop. Okay, if the pressure drop exceeds 2.5 psi, a TXV with an equalizer line should be used. Okay, so a TXV with an equalizer line should be used, and I'll show you a picture of this. The equalizer is used to compensate for that pressure drop, because again, our evaporator pressure is part of our forces that open or close the TXV. 2.5 psi is not a whole lot, okay? So, I mean, it's a very insignificant amount, but it does make a difference in that TXV. Distributors are octopus-looking things following the expansion valve on larger multiple-pass evaporators. Okay, the distributors distribute the refrigerant through the multiple passes. This is a distributor. Okay, basically, on your outlet of the TXV, it's split into different coils, different sections of your evaporator. So one evaporator might actually have 16 or 17 coils on it.
that the refrigerant is going to flow through individually. This is a residential or like commercial system. Okay, I have different portions of the coil. I have one portion here, one portion here, one portion here. Okay, each of these portions has actually 2 rows of coil in it. You see, if you look real closely, there's 2 distributor pipes coming over here. There's 2 distributor pipes on the center one. There's 2 distributor pipes on this third one. So the reality is that this system has 6 individual evaporator coil runs. Okay, and then it all joins together on the manifold. That comes back to the suction side. Okay, so a distributor basically takes the outlet of that TXV, the side that would go into basically the side that would connect to your evaporator, and it distributes it into what we call a multi-pass evaporator. Okay. Any questions on what a distributor does? The rate of flow of liquid through the TXV is directly proportional to the load conditions. The greater the load, the greater the flow of refrigerant through the TXV. The less load, okay, the lower the load, the less refrigerant through the TXV. Now, in a lot of cases, the greater the load, the more liquid or vapor a pump has to pump, the greater the amperage. Let me say that again. The more liquid or vapor a pump has to pump, the greater the amperage. So, the amount of liquid which after it vaporizes turns into the amount of vapor that is going through the compressor, it directly affects compressor amperage. Anybody want to tell me why a TXV is used when you want to talk about efficiency? Did I lose everybody?
Just.
Yeah, why do we want to, why does a TXV affect efficiency of a system?
Because regulating itself?
It's regulating itself, but how does it affect how much energy we are using?
The constant change?
Yeah, because if I don't have a high load, why should I pump as much refrigerant in the compressor? By pumping less refrigerant, I'm lowering the amperage. Everybody see that?
Yeah.
Okay, that's pretty important because that's why TXVs and some of these other high efficiency expansion valves are pretty important. Okay, TXV force that control a TXV, as I've said a few times, the sensing bulb, this is the downward force that will open the valve. Evaporator pressure creates an upward force that will close the valve along with spring pressure. Spring pressure is my adjustable component. It's the only adjustable part. Creates the upward force that helps close the TXV. It's the only adjustable part. That is a test question. What is the only adjustable part of a TXV? Spring. TXVs are designed to work at equilibrium. That basically means when they come from the factory, they give you that perfect superheat. Okay, there's 3 factors that affect the capacity of a TXV. The evaporator pressure, the pressure drop across the valve, and the temperature of the liquid entering the valve. The colder, the better. By adjusting the spring pressure, superheat can be changed. TXVs can be internally or externally equalized. I've talked about that. The larger evaporator coils, which we'll talk about when we talk about evaporator coils, okay, they have an extra line. Okay, externally equalized TXVs have 3 lines: the liquid line, the evaporator outlet line, and the equalizer line. With externally equalized TXVs, and I'll show you a picture of this, the bulb must be mounted between the evaporator outlet and the equalizer line. Okay, there's a very specific place that you can mount that evaporator bulb. Okay, and just to show you a picture of that, it's right there. Okay, we have my evaporator coil. We have our outlet of our evaporator. We put the bulb there, and we have that third equalizer line that goes to the TXV. Very important. If the bulb is mounted in the wrong place, it will not work.
So that's all, that suction line and that external equalizer line are all under direct pressure the whole time.
Yes, they're under the same pressures as the suction side. Now, the bulb line is not a direct pressure. Okay, this line here, that's based on the gas or liquid that's inside the bulb and the temperature of that bulb. It's separate from the refrigeration system.
I see. Yeah, I forgot that it's not actually physically connected to the suction line. It's just sitting on it.
It's clamped on it. Yeah. Clamped very tightly on it. Okay, folks, that is where we are going to leave off today. If you guys are following and taking notes on this slide set, anybody who's printed this set, there's a ton more slides on here. We are not ignoring them. I'm going to do evaporators, and then we're going to come back to this because it's not going to, the rest of this is not going to make a ton of sense until I touch on evaporators. Okay, so we left off on what I call slide 54. That's just on mine. We're going to do evaporators, and we're going to come back to this slide set. So don't get discouraged if you printed a lot of paper. Any questions on anything I covered today?
No, sir.
Okay, you guys have a great rest of the day. Same time, same place tomorrow, and we're going to talk about evaporators.
Hey, Chris, I